Welcome to another episode of AI 10X, brought to you by 10 Leaves.
Yeah.
Right now, somewhere over the Atlantic, an algorithm is making a microscopic adjustment to a commercial jet's wing flap.
Yeah, an adjustment so slight that the passengers won't even feel a thing.
Exactly. But by the time that plane touches down, that single, calculated micro movement will have saved hundreds of gallons of fuel.
It's really incredible.
Today, our mission is unpacking the source material from episode 68, Navigating the Intelligent Skies, to understand exactly how artificial intelligence is transforming the very nature of flight. So next time you look up at a contrail cutting across the sky or, settle into your seat for a cross-country trip, you will realize just how much invisible intelligence is managing that journey.
Right, because it is no longer just a pilot pushing a throttle and talking to a tower.
Not at all.
We are looking at a fundamental rewrite of the aviation architecture. I mean, the historical view of flying is heavily mechanical, right? It's like this brute force negotiation with physics using thrust, lift, and drag.
Yeah, exactly.
But the reality outlined in our sources reveals that modern aviation has basically become a masterclass in edge computing and data synthesis. The sheer volume of telemetry being processed to move an aircraft from point A to point B safely and efficiently now relies just as much on neural networks as it does on aerodynamics.
Okay, let's unpack this. Because to really grasp that shift, we kind of have to look at the ground game first. The source material highlights how AI operates as a proactive intelligence before the wheels even leave the tarmac.
Right, specifically through predictive maintenance.
Yeah. And to appreciate the leap here, we have to recognize the limitations of legacy systems. I mean, traditional aviation maintenance is largely like a binary of scheduled checkups or reactive fixes when a sensor finally trips the threshold limit.
Which isn't ideal.
No, not at all. It feels entirely different with this new paradigm. If we use a car analogy, the old way is like having a car that just flashes a terrifying check engine light mid-road trip. But the AI approach is like a smart car that warns you a specific belt will snap next week. So how does shifting from reactive to proactive maintenance fundamentally change the reliability of air travel?
Well, what's fascinating here is the underlying mechanism driving that predictive capability. Modern commercial aircraft are essentially flying data centers now. A single twin-engine jet can generate multiple terabytes of data per flight.
Wait, terabytes just from one flight?
Oh, absolutely. We are talking about tens of thousands of highly sensitive sensors capturing, thermal signatures, acoustic anomalies, pressure differentials, and microvibrations.
That's way too much data for a human to track.
Exactly. Human technicians, regardless of their expertise, just cannot monitor millions of intersecting data points to spot a degrading baseline. But an AI model trained on decades of historical flight data can establish a flawless digital baseline for how that specific engine should behave.
Under specific atmospheric conditions, right? So it's looking for the delta.
Yeah, precisely. The moment a compressor blade's vibration signature deviates by, say, a fraction of a millimeter from that established baseline, the AI registers the anomaly. It registers the anomaly, calculates the degradation curve, and forecasts the point of failure. It understands that a specific acoustic shift at 30,000 feet correlates to a bearing failure in exactly 40 flight hours.
That is wild.
So the system then automatically generates a maintenance ticket, orders the necessary part, and routes it to the specific gate where that aircraft is scheduled to land next Tuesday.
And the result of that proactive approach is a massive reduction in aircraft on ground, or AOG, time.
Yes, exactly.
The reliability of air travel increases exponentially because you eliminate the cascading delays caused by unexpected mechanical groundings.
You fix the problem before it's even a problem.
Right. Well, that seamless handoff from the tarmac to the air brings us to the actual flight operations. Because a perfectly maintained aircraft sitting at the gate is just potential energy.
True.
Once that plane hits the sky, it is subjected to an incredibly dynamic environment. So how does this invisible intelligence adapt once the environment becomes fluid?
So this is where we see the transition from predictive analytics to real-time dynamic optimization. And to understand the gravity of this, we really need to look at the economic and physical scale of jet fuel.
Right. Fuel is routinely one of the largest single operating expenses for an airline, accounting for billions of dollars annually.
Billions. When a commercial airliner is in transit, it is continuously battling aerodynamic drag and gravity, burning massive amounts of kerosene. Now, traditionally, flight management systems, or FMS, calculate a highly efficient route prior to departure.
But the FMS is calculating a route based on a snapshot of the weather from, like, 2 hours ago. And the sky isn't a static medium, It is a chaotic fluid.
Right, you have shifting jet streams, thermal pockets, barometric
And
changes.
the constantly altering weight of the aircraft itself as it burns off that heavy fuel.
Exactly. The traditional FMS provides like a static roadmap for a dynamic environment. Integrating AI into real-time flight operations changes that computational landscape through edge computing.
So the knowledge is most valuable when applied in the moment.
Precisely. Instead of relying purely on pre-flight calculations or trying to ping a terrestrial server with terabytes of data, which introduces latency, the AI models run locally on the aircraft's hardware.
Ah, I see.
Yeah, so these models continuously ingest real-time weather radar, satellite telemetry, and wind shear data. Then they merge that with the engine's current performance metrics and the aircraft's decreasing mass.
So it is dynamically recalculating the optimal trajectory against variables that are changing second by second.
Yeah.
But what does that optimization actually look like in practice? I mean, is it just telling the pilot to fly 100 feet higher?
Oh no, it is far more granular than altitude adjustments. The AI calculates the absolute most efficient thrust vectors, pitch angles, and speeds for a given microenvironment.
Really? So it's tweaking the angle of the plane.
Yeah, it might determine that reducing thrust by 0.5% and altering the angle of attack by a fraction of a degree will allow the aircraft to ride the edge of a tailwind more efficiently.
That's incredible. Those are calculations involving complex fluid dynamics and thermodynamics that must be solved instantaneously,
Right.
which is basically beyond human cognitive capacity to calculate manually while also flying the plane.
Absolutely. The human pilot might know a tailwind is there, but calculating the exact mathematical optimization of engine RPMs to maximize that specific tailwind at that specific gross weight, that's an algorithmic task.
And this is where the macroeconomic impact becomes clear. I mean, when an algorithm shaves off 0.5% of fuel consumption on a single flight through these continuous micro adjustments, the absolute volume of fuel saved seems minimal, right?
On one flight, sure, but apply that efficiency across a global network executing tens of thousands of flights every single day.
Right, the cascade effect results in millions of gallons of fuel conserved annually. The reduction in operational overhead is massive.
And don't forget the corresponding drop in carbon emissions, which fundamentally alters the environmental footprint of the entire industry. The AI is essentially weaponizing data to solve complex physics problems dynamically, generating efficiency at a scale previously thought impossible.
Here's where it gets really interesting, because everything we've discussed so far positions the AI as an incredibly sophisticated assistant. It diagnoses the engine, it plots the fuel-efficient trajectory, it handles the math.
Right, it's a co-pilot.
But our source material outlines a hard pivot toward what it calls the autonomous horizon. The text explicitly states that AI enables aircraft to navigate, respond to changing conditions, and make complex decisions with minimal human intervention.
Yes, that's a crucial shift.
And I kind of want to push back on those specific phrases, changing conditions and minimal human intervention, because when we talk about changing conditions in aviation, we aren't just talking about a headwind.
No, not at all.
We are talking about severe, unexpected weather events, sudden decompression, or uncontained engine failures. So are we looking at a future where the AI is essentially the captain during a critical emergency?
This raises an important question about the intersection of human psychology and algorithmic execution. Because, we are biologically wired to trust human intuition, especially in life or death scenarios.
Oh, absolutely. I want a human up there in an emergency.
Right. The idea of an algorithm taking control of a damaged aircraft carrying hundreds of passengers runs counter to our inherent desire for a human hand on the yoke. However, an objective analysis of aviation emergencies reveals why autonomous systems are so effective in these exact scenarios.
Because an aviation emergency is essentially a massive high-speed data overload, right? You have auditory alarms blaring, master caution lights flashing.
Exactly. And the physical sensation of the aircraft altering its pitch or roll, plus a barrage of changing telemetry on the displays. An emergency represents a rapid cascade of intersecting variables.
Which is a lot for a human to process all at once.
It is. The limitation of the human brain in these scenarios is task saturation. A highly trained pilot is still bound by the physical latency of the human nervous system and the cognitive limits of processing simultaneous streams of chaotic data.
So the pilot must perceive the alarms, interpret the data, formulate a recovery strategy, and manually execute physical commands to the flight control surfaces. And that process takes critical seconds.
Precisely. But an AI system does not experience panic. And it does not suffer from cognitive task saturation. It views a sudden loss of cabin pressure or an engine failure purely as a mathematical deviation from the nominal flight envelope.
So it just does the math.
Yes, it ingests the sudden drop in hydraulic pressure, the asymmetrical thrust, and the altered aerodynamic profile, and it computes millions of potential recovery trajectories in milliseconds.
Millions. That fast.
In milliseconds. It can manipulate the ailerons, elevators, and rudder with a level of simultaneous precision that a human pilot cannot physically replicate. The machine isolates the problem, calculates the aerodynamic boundaries of the damaged airframe, and executes the mathematical solution required to maintain lift and stability.
Framing it that way shifts the narrative completely.
Yeah.
It isn't that the AI possesses better judgment than the pilot.
Right.
It is that the AI operates outside the bounds of biological latency. It can process the chaotic data and stabilize the airframe infinitely faster, which means the pilot's role evolves, doesn't it?
It has to evolve. They are no longer the manual operator wrestling with the yoke. They become the systems manager. The AI handles the high-speed data execution, freeing the human to focus on the macro-level outcome.
Like communicating with air traffic control, running the emergency checklists, and deciding where to divert.
Exactly. The human manages the strategy. The AI manages the execution. It is the deployment of the optimal tool for the specific problem. High-speed, multivariable data processing during a crisis is an environment where artificial intelligence mathematically outperforms human reflexes.
Wow. Well, that partnership between human strategy and algorithmic execution works brilliantly for a single aircraft. But planes don't fly in a vacuum.
That's a very good point.
Our source text highlights the looming challenge of increasingly crowded skies. Because all that onboard intelligence, the predictive maintenance, the real-time fuel optimization, the autonomous recovery capabilities, it means very little if the aircraft is flying into a congested, unmanaged traffic jam at 30,000 feet.
Right, the airspace itself has to evolve.
Exactly.
If we connect this to the bigger picture, the global airspace is a massive, dynamic, three-dimensional puzzle. And historically, managing this network falls squarely on the shoulders of human air traffic controllers. We really have to respect the immense cognitive load required to do that job.
Oh, it's unbelievable. They are constantly projecting 3D trajectories based on 2D radar screens, managing the ascent, descent, and separation minimums of dozens of aircraft simultaneously.
Yes, they are mentally calculating the intersecting flight paths of metal tubes moving at hundreds of miles an hour, taking into account varying speeds, altitudes, and weather deviations. The mental gymnastics required to maintain a safe picture of that airspace is staggering.
It truly is staggering. And as the volume of global air traffic continues to accelerate, we are kind of approaching the upper limits of human cognitive capacity to manage that space efficiently, aren't we?
We absolutely are. When airspace becomes too complex for human controllers to map optimal continuous trajectories for every aircraft, they have to introduce inefficiencies just to guarantee safety.
Like implementing holding patterns or vectoring planes miles off course or enforcing ground stops. So safety is maintained, but the efficiency of the entire network degrades.
Exactly. Which is where intelligent air traffic management comes into play. The AI isn't just looking at a single sector of a radar screen.
What is it doing instead?
It is ingesting the telemetry of the entire airspace simultaneously. It knows the exact position, speed, altitude, and intended destination of every single aircraft in the network. It utilizes 4D trajectory management.
40. So that's 3 spatial dimensions plus time, right?
Yes, exactly. An AI system can project the flight paths of thousands of aircraft hours into the future. Let's say a human controller might resolve a conflict by putting an arriving aircraft into a holding pattern, forcing it to burn fuel while flying in circles.
Which we've all experienced as passengers.
Right. But an intelligent traffic management system identifies that same potential conflict when the aircraft are still hundreds of miles apart. It calculates that if aircraft A reduces its speed by just 5 knots right now, and aircraft B alters its descent profile by a fraction of a degree, the conflict never materializes.
So by making these microscopic adjustments at the macro level, the AI effectively prevents bottlenecks from ever forming. It doesn't solve traffic jams. It ensures the traffic jam never exists in the first place.
Spot on.
The flow of aircraft into a busy hub like O'Hare or Heathrow becomes a perfectly synchronized, continuous descent. No holding patterns, no wasted fuel, just a seamless integration of assets.
The result is a network that operates at peak capacity without compromising the safety envelope. The AI handles the sheer computational weight of mapping thousands of 4D trajectories, allowing human controllers to act in a supervisory role, managing the overall flow and handling exceptions that require strategic human input.
So what does this all mean? If we step back and synthesize everything we've pulled from today's deep dive, we are basically witnessing the complete digital reconstruction of the aviation industry. The source material delivers a really clear verdict.
It does.
Artificial intelligence is pushing aviation into entirely new territories of safety, efficiency, and innovation. We started on the tarmac, exploring how deep learning neural networks analyze sensor data to predict and prevent mechanical failures long before they disrupt a flight schedule.
And then we moved into the sky, seeing how edge computing transforms the aircraft into an invisible co-pilot, dynamically adjusting thrust and pitch against changing weather to save millions of gallons of fuel.
Right. And we analyzed the critical shift toward autonomy, recognizing that high-speed data processing allows an algorithm to handle the chaos of an in-flight emergency faster and more safely than human reflexes alone.
Plus, we zoomed out to see the macro-level impact, where intelligent air traffic management solves the massive 4D puzzle of our crowded skies, eliminating bottlenecks before they even form. It is a completely integrated intelligence ecosystem, from the maintenance bay to the stratosphere.
Exactly. Now, our source material left us with a glimpse of what is coming next. Having fundamentally optimized the movement of assets through the air, the next deep dive will focus on AI in logistics and supply chains.
Which is the logical next step. I mean, if algorithms can perfectly route thousands of high-speed jets in three-dimensional space, applying that same intelligence to cargo ships, freight trains, and global warehouses will completely rewrite global commerce.
It really will.
Yeah.
It represents the inevitable application of deep data synthesis to all physical movement. But before we close the book on intelligent skies, there is a lingering implication here from the experts' insights that warrants critical thought.
Yeah, we have spent this deep dive establishing that artificial intelligence is fully capable of navigating, optimizing, and managing the incredibly chaotic, high-stakes, life-or-death environment of commercial aviation, often with minimal human intervention.
Which is a huge realization.
It is. If an algorithm is robust enough to captain a damaged jet through a severe weather event and land it safely, we really must reconsider our assumptions about other industries. What other incredibly complex, seemingly human-only systems in our daily life, systems we currently assume require human intuition, oversight, or management, are actually on the verge of becoming completely autonomous?
That is a brilliant and perhaps slightly unsettling thought to walk away with. It absolutely challenges you to reevaluate the complex systems operating quietly in the background of our everyday lives. And as we wrap up, we want to welcome to another episode of AI 10X, brought to you by 10 Leaves. Even as we say goodbye, see you next time.